Today I'm going to speak about very simple solutions of the Navier-Stokes equation. You may be familiar with very complicated or somehow less complicated solutions, but today, as you see, I have written here 6 fundamental solutions of the Navier-Stokes equation, which are helpful to increase your sensation about the Navier-Stokes equation and balance of forces in this important equation. Okay, this is the full Navier-Stokes equation, including the local derivative term, which shows the steadiness of the problem. The second one is the advection term, which is the nonlinear acceleration. And the third one is the relative accelerations, such as the Coriolis acceleration or the centripetal acceleration. The first one on the right-hand side is the pressure term. The other one is the gravitational force or force density term. And the last one is the divergence of the viscous stress tensor, which turns to be the product of the viscosity, the molecular viscosity, and the Laplacian of the velocity field for incompressible flow with constant properties. So this is the divergence of the stress tensor, viscous stress tensor, or the viscous term. I'm going to compute 7 quantities for all these 6 types of flows. The first one is the local derivative, the advection, and the relative derivative. The other quantities are the divergence of the velocity field, which shows the compressibility of the flow field. The other one is the curl of the velocity, which indicates the rotationality of the flow field. The sixth one is the viscous stress tensor itself, which helps us to judge about the viscous effects in flow. If the viscous stress tensor is 0, it means that the flow is inviscid. And the 7th one is the divergence of that stress field, which shows the resulted force density from the stress field. So if the divergence of the viscous stress is 0, it means that the last term in the Navier-Stokes equation is 0, but the viscous effect exists in the flow field. For the sake of clarity, this is the relation between the viscous stress tensor and the strain rate tensor or the deformation rate tensor, which is a linear relation based on the Stokes equation, constitutive relation, or the Newton's viscosity law. And also, if you remember from the continuum mechanics course, that the gradient of velocity can be decomposed into 2 parts. The first one is exactly the deformation rate tensor, and the second one shows the rigid body rotation or the rigid body motion, which is called the rotation tensor, which is antisymmetric. The first one is symmetric and the second one is antisymmetric. Okay, let's start from the first solution of the Navier-Stokes equation, the simplest one maybe, which is the fluid at rest or the static fluid. As you see, the velocity vector is 0. When all these quantities are all 0, the divergence of the velocity, the curl of the velocity field, the relative accelerations and other accelerations, and also the quantities related to the viscous stress tensor are all 0. The second one is the rigid body linear motion. So based on this part, which is the linear motion, we don't have the centripetal acceleration. So the relative velocity, again, the relative acceleration is 0. And we just have the local derivative, since the velocity varies with time, but different points in the fluid don't have a relative velocity with respect to each other or with respect to spatial coordinate. And the velocity is just, the velocity of all points in the flow field is just a function of time. So, again, the last term in the equation is 0. And in the rigid body linear motion, the pressure term and the gravitational term, which are similar to each other. Sometimes in some literature, we call these two terms as a single term. Okay, in the rigid body linear motion, there is a balance between the local acceleration here and the pressure and the acceleration terms in the right-hand side of the equation. So, as you see, we have equal velocities at a specific instant of time for all points in the flow field, but the pressure varies in the flow field. So you can see as if the flow accelerates, the free surface deforms, and the depth of the fluid particle placed on a horizontal line decreases by increasing the x coordinates from left to right. The third solution is the rigid body rotation or the forced vortex. I've already recorded a video about the vortex, different types of vortices, and we have two vortices here, the free vortex and the rigid body rotation or forced vortex. This one in different elementary fluid mechanics textbooks is classified among the static fluid, but this one and also for the solutions number 4 and 5 are mentioned among the potential flow solutions. Okay, let's find out what the reason is. The rigid body rotation or the forced vortex, as you know, something like this. We have a glass of water which rotates, and the free surface deforms like this. And as you see, by increasing the radial coordinate in outward direction, the depth of water increases, so the pressure of the fluid increases, and also based on the well-known relation R omega, which shows the velocity of the fluid in theta direction or in peripheral direction. Again, the velocity increases, so both the velocity and the pressure are increasing. This is the velocity vector, 0 and 0 in radial and z directions, and r omega in theta direction. The local acceleration is 0 because the flow field is steady, and the relative acceleration exists based on the centripetal acceleration is equals minus r omega squared in radial direction, inward direction, of course. Pay attention to this minus line here. And you can easily compute the advection derivative in polar coordinate. Of course, you have to know different types of operators in polar coordinates, including the divergence operator or the curl operator, the divergence of the tensor, and of course the stress tensor in polar coordinates. And here the advection term or the nodal operator or the del operator in you can compute the advection term which equals 0. So different points have different velocities in this example, but the advection term, which originates from a relative motion of particles with different velocities with respect to each other, is 0. So the flow is a rigid body rotation like a solid. The divergence of the velocity field is 0, so the flow can be regarded as an incompressible. And the curl of the velocity field is not a 0. I strongly recommend to compute the curl of this velocity field in polar coordinate as a good exercise. And you'll find out that the curl is just in z coordinates because the flow is rotating like this, and the vorticity is in z direction based on the right-hand rule. Twice the angular velocity of the flow. And viscous stress tensor is 0, so the flow can be imagined to be inviscid because the viscous stress tensor vanishes. And the Laplacian of the velocity field is expected to be 0 because this is the divergence of the stress field, which is 0. So the divergence of 0 is 0, but you can compute the Laplacian operator in polar coordinates, and you can obtain, this is the Laplacian operator in of a vector, of course, pay attention to the computation of the Laplacian of a vector in polar coordinates. Yes, the result is 0, so the flow is the viscous force term is 0. The flow is inviscid. The flow is rotational and incompressible and also inviscid. And as you see, the advection acceleration is 0. Based on these relations in Navier-Stokes equation, the pressure and the gravitational terms are balanced with the relative acceleration, which is the centripetal acceleration. We have a flow like solid without the viscous stress tensor or inviscid flow. The pressure is balanced by the centripetal acceleration, and the Bernoulli's equation in our direction is not valid anymore. As you see, pressure increases in a horizontal direction. The pressure and the velocity both increase. And the fourth solution is the free vortex or the vortex potential. The velocity field is like this. Again, we have the velocity just in the peripheral direction, and two other velocities are 0, and that non-zero velocity field is just a function of the radial direction. Here r equals 0 is the singular point of the problem, and also this point is valid for the next solution. We have c over r here. And the divergence of the velocity field is 0, so the flow is incompressible. The curl of the velocity field is 0, which shows that the flow is curl-free or irrotational. And the advection term is again 0, so different points in the flow field have different velocities with respect to each other, but the advection acceleration is 0. But the important point here is that the viscous stress tensor is not 0. I have written the formula of the stress tensor in r and theta direction. You can easily substitute the velocity vector in this relation, and you will find out that the viscous stress tensor is not 0. This element of the viscous stress tensor is not 0. The divergence of the stress tensor is 0. It means that the flow is viscous, and the viscous stress tensor contains non-zero element component, but the divergence of the stress tensor vanishes, which is proportional to the Laplacian of the velocity field. Again, it's not 0 due to existence of the centripetal acceleration. The Bernoulli's equation is valid. As you see, this is the Bernoulli's equation in a horizontal direction, neglecting the gravitational force. You can replace this, the gradient of pressure based on the Navier-Stokes equation. We don't have this term here, and also the gravitational force. And the relative acceleration equals minus the gradient of the pressure. So the gradient of pressure equals squared velocity over r. You can easily substitute the velocity, which equals the product of r and omega here, and you will see that the Bernoulli's equation is valid, is satisfied. And so here we have an incompressible, irrotational, and viscous flow, which is called the viscous potential flow, because the flow is curl-free potential, but the viscous stress tensor is at 0. But its effect, which is the viscous force in Navier-Stokes equation, disappears. This is the deformation of the free separation. As you see, this is the axis of rotation, which is a singular point. By moving in outward direction, the velocity increases, but the pressure, the velocity decreases, but the pressure increases. The fifth solution is the sink or source solution, which is again one of elementary solutions of the potential flow theory. It is similar to the previous one, but this time the velocity of the radial direction is non-zero, and two other velocities are 0. The divergence of the velocity field is 0. The curl is 0 because it's a type of potential flow. And this time the components of the viscous stress tensor, the diagonal components in r and theta directions are not 0. So similar to the previous case, we have a non-viscous flow or implicit flow, and the Laplacian of the velocity field is of 0, but this time the advection term in the Navier-Stokes equation is non-zero. So in the Navier-Stokes equation we have a balance between the pressure term and the gravitational term, maybe, sometimes, and this time the advection term. So because we don't have the relative acceleration here, because the source or sink is a linear motion of a fluid particle, but this time we have the advection term, and the Bernoulli's equation is valid. You can again replace the velocity vector in this relation, the velocity vector of the sink or source term in this equation, and you will conclude that the Bernoulli's equation is valid. Similarly, you can replace this velocity vector here for the rigid body rotation or the force vortex in the Bernoulli's equation. Pay attention that in the case number 3, again we have the centripetal acceleration, so the pressure term is equal to V sub r squared over r. And the last one is the well-known Couette flow, which has a linear velocity profile, something like this: flow between two infinite plates. The lower plate is fixed, stationary, and the upper plate moves at constant velocity u. So we can obtain that the velocity field is linear, increasing from 0 and reaching the velocity of the upper plate in Cartesian coordinates. Again, we obtain that the velocity is incompressible, the flow is rotational, and the curl of the velocity is in direction which is normal to the board. You see, this is an element of the fluid. The lower side of the element moves at a lower velocity with respect to the upper side, so that element has to rotate in minus z direction based on the right hand rule inward the board. And the viscous stress tensor is non-zero because of existence of non-zero shear stress in x and y direction. So tau sub xy equals mu c, which is a constant. As you know, the shear stress in the Couette flow is a constant, so the flow is viscous. But when you're computing the divergence of the viscous stress tensor, which equals the Laplacian, which is proportional to the Laplacian of the velocity, is 0. So in Couette flow, and the flow is without acceleration. So of course the fully developed Couette flow is this term is 0 just for the fully developed parallel flow Couette flow. So we have again viscous flow with 0 viscous force in the Navier-Stokes equations and 0 acceleration, and incompressible and rotational flows. So we have a rotational viscous flow here without the viscous term in the Navier-Stokes equation, but here the viscous stress tensor is not 0, and again the viscous term in the Navier-Stokes equation is null, but as you see, the flow is potential and curl-free and irrotational. At the end, I have written the components of the viscous stress tensor in r and theta. And these are diagonal components in polar coordinates. You may use them to drive these relations.